Pleasure to introduce Pierre Weiss, who will talk about representative theorems in convex optimization.
Thank you, and thank you for the invitation. I'm very pleased to be here. So today I will talk about representative theorems in convex optimization, and I'm pretty sure that everybody know what is the standard representative theorem, but I will just reintroduce you, and I'm sorry if it's a bit trivial for you. And actually, we will try to extend it to convex optimization. So this is a research work that was born actually in Cambridge, like more than 1.5 years ago, from a discussion between Antonin Chambolle and Pierre Weiss that I was attended, and then people joined this work. So also Yohann De Castro and Vincent Duval, who are in Paris, and Frédéric de Gournay, who is in Toulouse. Okay, so the more, the merrier. And right after we posted this work on archive, we found that Christian Bredies and Marcello Carioni had some similar results. So I know what you're wondering about is what is the transportation map of intelligence measure between Christian Bredies and Marcello Carioni between all these people. And I would say that it's unbalanced optimal transport because all these people are really smart. Okay, so let me just remotivate or reintroduce what are representative theorem used in machine learning. So it comes from the machine learning community, and actually it characterizes structural properties of minimizer, okay? Minimizer of the regularized empirical risk, and it characterizes it without actually needing to solve the problem. This is a nice result because actually if you want to work in an infinite dimensional Hilbert space, the structure given by the representative theorem will help you to recast the problem in a finite dimensional problem, and then you can actually solve it on a computer. You will see what I'm talking about right after. And so it explains the practical success of kernel method in reproducing kernel Hilbert spaces. So just to fix the idea rapidly, if we take like a very easy problem in machine learning, which is the problem of a support vector machine, where you want to find a separating hyperplane that separates the blue points from the red points. So I would say that my points are just individuals characterized by some variable xi, and that the color is encoded by the label yi, and I just choose 1 for the blue and -1 for the red ones, okay? And so I want to separate those points that I know, and I know that those points are blue and red, right? And I want to separate them using a very simple classifier, which is linear and which is in hyperplane. So just to be robust to some outliers coming, if I want to do prediction in the sequel, I want to find the hyperplane which has the largest margin. The largest margin means that I want to maximize the minimal distance between the hyperplane here and the first points in the blue group and the first point in the red group, okay? Just to be more robust. Okay, so if you parameterize the hyperplane by some normal vector W, you can write this problem. So actually you want to maximize the margin or minimize the squared L2 norm of W such that under the constraint that you classified well everybody, okay? So such that the blue points are on the right and the red points are on the left. So once you have written this problem, you can write its dual, the associated dual problem here. So you have the alpha I to be the dual variables, and both problems actually can be solved here on a computer because we are in finite dimension. But the nice thing is that you know that now the decision frontier that you will use to predict the color of a new point will be linear in linear like this. So you will just choose the sign of a sum of linear function in the new points that you want to predict if it's blue or red, okay? So it's really a simple way to classify, and I know that you're going to say, okay, but in practice, data are not always linearly separable, right? But I don't want to throw away all this machinery because it's pretty simple, and actually it's really easy to implement it on a computer. And so I want to see if I just can extend this linear classifier to non-linear ones in an easy way. And this is really the purpose of kernel method. So imagine that now you have this kind of configuration between your points. So of course you cannot find an hyperplane separating those points, but you can just lift the problem to a higher dimensional space, or maybe to an infinite dimensional space. And in this lifted space, maybe the data are separable. So I just stole this picture. Imagine that you're starting from this, then you lift the problem in R3 with a polynomial kernel, right? And now in R3, this data is becoming linearly separable with a hyperplane, okay? So this is really the core idea of kernel method in machine learning, and actually you can just extend what you did with linear classifier to non-linear ones. So if you now considering reproducing kernel Hilbert space H, associated to the map phi. So phi is just taking raw features, so the native individual if you want, and they bring you to the lifted space, so the Hilbert space. And reproducing kernel Hilbert space has the nice property to come with the kernel K, where K is able to encode the scalar product in the Hilbert space, right? So in practice, I will never use phi because phi can be really complicated to compute, okay? But I know that in the complicated space, the higher dimensional space, or even the infinite dimensional space H, I have a way to compute this scalar product here, okay? And so actually, I can just try to rewrite my support vector machine with now not directly my features, my initial features, but the transformed ones. And as you see, it's really easy because in the dual problem here, here the features, the variable xi and xj were present here only by scalar products. And it means that I can really translate these dual problems in the RKHS using this kernel here, because this one is really easy to compute in practice on a computer. Okay, and yeah, and again, I can say that the decision frontier now will be written as a sum, so the sign of the sum, a finite sum of some function given by the kernel, okay? So it's really an easy way to extend linear classifiers to nonlinear ones. So far I've not cited the representer theorem, so if I want to state it in a more formal way, I could say this. So if I consider some loss function L and any non-decreasing function G, and that I'm looking at the minimizer of the loss function of my data points, regularized here by a function of the norm of the Hilbert space that I'm considering, I can show that this problem admits a solution of this form, okay? Because I got initially n points in my training set. I know that a minimizer can be written as a finite sum until n, a finite combination of functions that are easy to handle. And actually, if big G here is strictly increasing, then any solution has this form. So you can really see the power of kernel method here, because this representer theorem tells me the structure of the solution. Then I can just plug this in my SVM problem, and I just have to solve a finite dimensional problem to find here the coefficient alpha I, okay? Okay, so this is a standard statement for representer theorem in machine learning, and actually we want to extend it to more general convex optimization problem. So, but before doing so, I'm pretty sure that you already know representer theorems in some convex problems, and in particular in signal processing. So if we look at the basis pursuit problem in the vector case, so I want to reconstruct a sparse vector. I have access to some measurements y. I have m measurements y that are given through a measurements operator phi. And I'm just looking at the solution of the minimum L1 norm such that I have equality constraint to my measurements. I can show that this problem, the basis pursuit problem, admits a solution which is m sparse, where m is really the number of measurements that you got. Okay? So, of course, it's interesting if m is less than the ambient dimension of my vector. Okay? And actually, this result also holds for the regularized version of the basis pursuit. Assume that you have maybe some noise in your measurements, and you want to solve now the regularized problem p lambda, where you just add a data fidelity term here between the observation vector and the mapping of the signal x through phi. And why it's so? It's because, okay, you can really solve p lambda, and let's call the x hat a solution of p lambda, and you can just plug here, instead of y, you put phi x hat, and you know that for this problem you're going to have a solution which is m sparse, and which is going to be also solution of this problem. Okay, so I will only focus on this kind of problem here, okay, with equality constraints, but keep in mind that the result that I will state can be really extended to this form of problem. Okay? Okay, let's move on. Another one is the continuous basis pursuit. So now I don't want to reconstruct a vector, a sparse vector, but I want to reconstruct a discrete measure. And by discrete measure, I mean just a finite sum of Dirac masses. Okay? So now I'm in the domain X, which I assume to be compact. I have some measurements phi mu from my measure that I want to reconstruct here, and this is just the integration of some continuous function against my measure that I want to reconstruct. Okay, and I have m measurements like this, m integration of continuous function against this measure. So I can try to minimize here the radon measure, or the total variation norm of my measure mu under equality constraint with my observations. Okay, so just to remind you, so the total variation of a measure can be defined like this. Okay, by duality on the set of continuous function equipped with the L infinite matrix, and so it's really the continuous basis pursuit, because if you consider a discrete measure that admits a form of a sum of n Dirac masses, the total variation of mu is just the L1 norm of the amplitudes vector. Okay, you're just summing the amplitudes in absolute value, and if your measure mu admits density with respect to the Lebesgue measure, then your total variation is just the L1 norm of your density. Okay, so this kind of problem have been considered in a paper from Yohann De Castro and Fabrice Gamboa, also Christian Bredies and Pekka Heinen, and really Emmanuel Canes and Carlos Fernandez Granda popularized it with the super resolution term, but I mean all these kind of problems are the same, and you can call them deconvolution, frequency estimation, line spectral estimation, or super resolution. Okay, or continuous basis pursuit if you want. Okay, and yeah, just to say to you that this is a really, really old problem from the 30s that is due to Krein and Berling, and these guys were interested in the generalized moments problem, where you have the first, well, the moments of a measure that is given, and you want to find the corresponding measure. Okay, so there exists representative theorems for this problem. The oldest one that we found is due to Ziovicki. He's saying that there exists a solution of the continuous spaces portrait of this form. Okay, so with a number of Dirac masses, which is m, where m is again the length of the observation vector. And Fischer and Jerome strengthen the result by describing the extreme point of the solution set, and by saying that all the extreme points can be written like this. So it's stronger in this way. So if you recall what is an extreme point, so an extreme point of a convex set is just a point that cannot be expressed as a convex combination of two other points living in the convex set, right? So on this figure, I have E0, E1, E2, E3, E4 to be extreme points, but also all the points on the semicircle, okay? And you have the Krein-Milman theorem saying that if you're considering a Hausdorff space, then your convex set is compact, then your convex set can be really seen as the closure of the convex hull of its extreme points. So in this sense, describing the extreme points is stronger than just exhibiting some solution which has this structure, because once you have the description of the extreme points, then you are able to reconstruct any solution to your problem. Okay. And then Michael Unser and also Axel Flint and Pierre Weiss, Michael Unser and co-author, extend this kind of result by considering here a surjective operator L, and by working on a functional space and just looking at LU, where LU lived in the radon measure space. Okay, so it's just an extension of this kind of work. And so how we have seen, so minimizing the total variation tends to promote Dirac masses in the solution. And this actually has motivated some algorithm. For instance, in the paper of Christian Bredies and Pikkarainen, but also in the paper of Quentin de Noyelles and Vincent Duval, you can really, since you know that you're looking for a solution that has this form, you can really parameterize your problem by this, and then you can run a conditional gradient method or a Frank-Wolf method by adding at each iteration a new atom, okay, new Dirac masses to your solution at the current iterate. And so we would like to know how general is this phenomenon, and can we do the same for other types of regularization, such as the total variation of the gradient and not the total variation of a measure. So one key observation that should be done at this step is that in the spirit, actually, of the paper of Chandrasekaran and co-author, the convex geometry of linear. Yeah, sorry, I forgot the title, but yeah, this is the first words are correct. So we have to remark that the one sparse vectors are the extreme points of the L1 ball, okay, in the finite dimensional case. And so we are saying that when I want to minimize the basis portrait, I know that I have some solution that can be written as a sum of m, the number of measurements, m vector in the canonical basis, because this is m sparse, so m extreme points of this ball, okay? And again, in the continuous setting, I have the same thing. I can say that Dirac masses are the extreme points of the TV ball. And again, when I'm solving the continuous basis portrait, I can say that I have a solution which is a sum of m Dirac masses, so m extreme points of this set. Okay, so let's try to write a theorem like we asked to Santa Claus. Okay, so we want to minimize generalized regularizer here, function r in U. We want U to live in a Barnard space, to be very general, and we have of course equality constraints to some linear measurements. Okay, phi is assumed to be linear, and we would like to have that every extreme point of our solution set is the convex combination of at most m extreme points of the sub-level set, okay, associated to the regularizer, and which is less than the minimal value of p. Okay. So if you want to write this kind of result, actually, if you will need, for the existence of minimizer, you will need that this space, this level set, sorry, is compact. And if you want this level set to be compact and to hold for the norm of the Barnard spaces, then you have to consider locally convex vector space and not Barnard space, and to require the continuity of phi. Okay. So here it seems that you have to do tricky assumptions, right, to have the existence of the minimizer and to have this description with extreme points. So the choice of the topology seems crucial, and we didn't really want this kind of results because we thought that the description of the extreme points was really a geometric feature of the problem and not a topological one. Okay, but still we work hard to have this kind of result that we didn't publish. Okay, and then Vincent Duval, who was really a driving force on this project, finds a series of paper of Dubins and Clay in the 60s, which killed the game actually for us. These are really nice paper, you know, the kind of paper that are 8 page long and with 2 references in the bibliography, so really smart and really dense. So I just need some definition to state them, to state their result. So I will consider a vector space E a convex set C. I will say that C is linearly closed if for any line L, the endpoints of the intersection of the line with the convex set belong to C. Okay, so here this is the case. This is the intersection of the line with C, and the endpoint here belongs to C. Okay, and I also need the notion of extreme ray. So an extreme ray is just a half line, and where I take a point on this half line of C, I can only express a point on the half line of C as a convex combination of 2 points living also on this half line. Okay, so in this picture, it's really just the blue part. Yeah. Yes. Okay. And this is the Dubins-Clay theorem. So if I have a vector space, a convex set C, which is linearly closed and which contains no line, if I have an affine space F of codimension M, so think of it as my admissible set, okay, my feasible set, then each extreme points of the intersection is a convex combination of at most m plus 1 extreme point of my convex set, or a convex combination of at most m points, each an extreme point or in an extreme ray of C. What does it mean? So here I'm considering this convex set C in gray. I have this affine space F of codimension 2. I look at the intersection of C and F. I look at the endpoints, which is here, and I need 3 extreme points of C to express this red point. Okay? Now I take another configuration. Okay? I have still an affine space of codimension 2, but now these endpoints can be expressed as a convex combination of 2 points living on extreme rays. Okay, so I'm in the second point, the second item of the theorem. Okay, so this is exactly what I need for my problem. Yeah, and just before getting to this, we should remark that we don't study the existence of the extreme points. Okay, it's implicitly assumed. You have to check it on your own. Okay, and if actually you have extreme points for the intersection, it means that you have also extreme points in your convex C. And which is nice is that it deals with the unbounded case. So we can really apply it to a particular problem. So if I go back to the continuous spaces pursuit, so E is my radon measure space. F is an affine space of codimension M. So this is the admissible set, okay, the feasible set. And I choose my convex set to be the sublevel for the total variation associated to the level of the minimal value of my continuous spaces pursuit. And I know that the solution set of the continuous spaces pursuit can be written as the intersection of those two. Okay? And then I apply Dubin's and Klee theorem, and I can say any of its extreme points can be written as a sum of, here, m plus 1 extreme points of C that I know to be the Dirac masses. So why do I have to pay a plus 1 here, whereas I know that I only need m, right? M Dirac masses. It's because the Dubin's and Klee theorem can really handle any configuration between C and F, the affine space. But when you are minimizing a regularizer such that you have equality constraint, you are not doing, it's not in, well, in general, there is something that does not happen, and I can do it on a graph here. So we are in 2D, we have here an affine space, okay? And I want to minimize the L1 norm. And I can really take the gauge view of the L1 norm. So minimizing the L1 norm means that you're going to inflate the L1 ball until you reach an admissible point in the affine space, okay? So again, diamonds today. There is a lot of diamonds. I could say that this is the girl's best friend, but you use it too, so I cannot. Okay. And so you see that here, actually the sublevel set, you inflate it until you become tangent to the affine space. Okay, so this is not any configuration between those two. And so this is why we are trying to illustrate in this picture. So here, of course, we are not in this case, but when you minimize usually the L1 norm or the total variation, you are more likely in this case, okay, when you are tangent. And in this case, you really need here to express this point only 2 extreme points of C and not, as before, 3 extreme points, okay? Okay, so that's it. So we have our theorem. So if we are in a vector space, we have a convex function R, linear measurements, such that the solution set is non-empty. We assume that the sublevel set associated to R is linearly closed and contains no line. Then, and also we require that the minimal value of the problem is strictly larger to the infimum of the regularizer. Then each extreme point of the solution set can be a convex combination of at most m extreme points of the sublevel set, or a convex combination of at most m-1 points, each an extreme point, or in extreme rays, of the sublevel set. Okay, and what happens if you have equality here between the minimal value of P and the minimal value of the regularizer? on your space, then you have to pay an extra point here. Okay. Yeah. So this is tiny details, but. Okay, so just idea of the proof, which is really basic. Once you have Dubins and Klee in your pocket, you just show that each extreme point of the solution set belongs to a face of the sublevel set of dimension at most m-1, and then you invoke the Klee's extension of Kara-Theodori theorem for unbounded sets. Okay. Okay, and yeah, we just recall here. The Klee theorem. Okay, so let's take example and reapply our theorem to standard problems. So for the continuous spaces portrait, you will find that again you have this structure in the solution. You can also study here the feasibility problem. So here you're looking for a measure mu which is positive. Under the equality constraint again, and right now you need m+1 Dirac masses. Why do I need m+1 Dirac masses? I know that everybody wants wine, but just to see if you were attentive. No, you need m+1 because this is equal to 0 if mu is positive, and this is equal to plus infinity if it's not. So the minimal value of the problem here is equal to the minimal value of this function here. Okay, so you need to pay an extra point. And again, but here again a feasibility problem, but for matrices. So if you're looking for a symmetric, semi-definite positive matrix under equality constraint, then you can say that again you will need m+1, a sum of m+1 rank 1 matrices here. So again you need m+1 because here you reach the minimal value of the regularizer. Okay, just a word to say that our result is clearly suboptimal in this case, because if you have the information that maybe your matrix that you're looking for is of rank R, then it's clearly suboptimal to have m+1. And of course it's useless if m is bigger than the number of rows or the number of columns in your matrix. Okay, so just is just a slide here to say to you that understanding the faces of C can be the faces of the sublevel set can be really helpful, because if you know that your matrix has rank R, then you know that you can decompose your matrix like this, right? So how can you use our result still? You can just start the proof of the result and you just plug this information, which is when S has rank R, it belongs to a face of dimension D which scales like this, okay? So you just plug this information in the proof and you will end with a description which will be like this, okay? And not suboptimal as our result. And actually it coincides with the known results due to Barvinok as far as we found. Yeah. Okay, so this is really the take-home message here. So the extreme points of the solution set belong to a face of your sublevel set of dimension at most m-1. But of course, if you have more information on the face, you have to use it and to plug it actually in the proof. Okay, and that's how you can have a sharper result than Kara-Theodori and Klee theorem. Okay, so let's do rapidly, really quickly, a new application to an old problem actually. So now we are looking to the total gradient variation of some function u. So it can be defined like this, okay? And it can be used to deblur or to denoise images. And we use it to in Spirit to promote smooth part on your images and sharp transition for just the border of objects in your image. Okay, so we're trying to minimize the total gradient variation of our function u such that we have equality constraint with our measurements. And then we need to understand what are the extreme points of the TV, the total gradient variation ball, okay? So we have results from Fleming and Ambrosio, Casillas, Masnou, and Jean-Michel Morel saying that the extreme points of this ball are the functions that are indicators of simple set, okay? Of course, renormalized by their perimeter because the total gradient variation of an indicator of a set is just the perimeter of the set, okay? Alors, what is a simple set? So I didn't define properly what is a simple set, but just with my hands, I can tell you that they are simply connected sets in the measure theoretical sense, and so simply connected and with no hole, okay? So just to give you why you cannot have many levels in your function is just because when you have many levels in your function, you can really decompose this function into two parts and express this function as a convex combination of those two parts. So, of course, you need your extreme points to have only one non-trivial level set, okay? So, first, I know that they should be indicator function of set. So, why do I need the set to be connected? Again, because if it's not, if I have two parts in E, I can again do a decomposition, and I'm not an extreme point. And why do I need to have no hole? Because if you have no hole, you can do this decomposition here with the minus on E2, and you are not an extreme point because you could be expressed as the linear combination of those two. Okay? So it's just for the intuition. And so it's a really nice result because it's saying that the extreme points of the solution set can be written as sums of at most m indicators of simple sets, so like this, and it can be seen as an explanation for the staircasing effect that is known in image processing when you're using such a regularizer. Okay, I think I'm off of time, right? No, that's okay? Okay, so just to illustrate a bit, so we just discretize the problem. Of course, I presented to you the problem in a continuous way, but you can discretize the problem, run a Chambolle algorithm, and if you have three measurements on some solution, on some function u, this is a TV reconstruction, and you can see that here we found three simple sets, right? Okay, so it's just a proof. It's not a proof, but okay. And we have ongoing work going on. It's about understanding actually the phases of the total gradient variation ball. So we were afraid that on the surface of this ball, some finite dimensional phase could be spanned by an infinite number of extreme points, okay, like a nasty face, and actually we found that if my face on the surface of this ball is a k-dimensional face, then I can show that it has finitely many extreme points. So this is a polytope, okay? Yes. So I don't know if you're interested, but we were. So and also, we wanted to characterize the one phase. Okay, so the one phase of the total gradient variation. So we want to. So we know that the extreme points are indicator function of simple set. Okay, so now I take two indicator function of two different sets, and I want to know when those two are giving me a one-dimensional phase. Okay, so which one? So here I have two simple sets. Okay, so what is your bet? It's too late. Which one? Sorry?
Bottom right.
Both on right?
Bottom right.
Bottom right? No, here? Yeah, sorry. So you think that this is going to give me a one-dimensional face? I'm sorry, I think no. Yeah. So maybe, okay. So sufficient condition. If I know that this is a face, then I know that when I'm looking at A minus B, then I should have 0 or the contrary, right? Or if the intersection is null in the measure theoretical sense, and that I have this Hausdorff measure of this frontier to be 0, then it's fine. But this is not necessary and sufficient condition. To have necessary and sufficient condition, I need to have A minus B to be indecomposable. So this is this one, okay? A minus B here is decomposable, so I cannot use it. So just to give you some intuition why you cannot have this one, for instance, to be a one face, is because when you are looking at, so you have A and B, okay, like this, A and B, and you're looking, so here you have, sorry, it's too, and you're taking a point which is right in the middle of the segment, okay? The one which is right in the middle of the segment can be really expressed as a combination of two other indicator functions, which are A union B, here, and here, just A intersected with B, okay? So here, we have again a diamond. But so this is more a two-face than a one-face, okay? And okay, and the last result that really motivates actually all of work, but which is not out yet, is that when you are an extreme point of the total variation solution set, you can show that the simple set that are at the structure of your solution are not in any configuration. You always have at most m+1 nodes. So it means that you should comply some embedding in your simple set or some disjoint property. Okay, you cannot have as many configurations as you want. Okay. Okay, and I will just stop here. So thank you for your attention.
Thank you very much. Questions?
That issue very important, the representer theorem. But the also important issue is how to find those extreme points of solution. So you mentioned when you were talking about this one minimization.
L1?
Yeah.
Yes.
You mentioned that the alternative way is Frank-Wolf algorithm.
Yes.
Which is actually a greedy algorithm. Is something similar to that exists for this total variation?
Yes. I mean, you mean of the gradient? Of the gradient, no. But we would like. But no, it's pretty hard to design an algorithm to have a Frank-Wolf strategy for it. But it would be really nice to have it. But I think it's hard.
Yeah, the problem there is also the total variation. It's again like a 1 over infinity. It's not a smooth Banach space. So
yeah.
Really
and you can move, actually, you have to move the frontier of the simple set, so it's going to be hard. But, yeah.
Other questions? Everybody is going
Yeah,
yeah, thank you very much.
Thank you.